Assalamu alaikum viewers. In today we are going to discuss the mathematical induction with respect to some examples. So what exactly mathematical induction is, it is basically a special way of proving a theorem by showing that if it is true for any particular case, then it is true for the next case in series. So how we basically prove a particular number series with the help of our mathematical induction process. For that purpose, I'm going to put down a few examples here, and with the help of that, we are going to understand this entire methodology of mathematical induction, how we induce the result with this mathematical process. So let's have a look at the first example. Okay, now here we are having a certain question, and a particular series is given to you, and we have to show that the sum of all these numbers, which is having this general form, when we sum up all these numbers up to n terms, the summation should give me an answer which should be equivalent to n squared. Now remember that whenever we discuss the summation of the terms of a certain sequence, that is called a series, you know that the sequence is actually a function that has a domain, natural numbers. Okay, so if I just say, okay, so you see sequence is a certain function, and the domain of this function starts from a natural number. This way how we represent the natural numbers notation, and it maps into a range, and range covers all real numbers. So sequence actually is having a domain containing a natural numbers only, and the range is going to be the real numbers. So here you can see that this general form is actually a sequential function. Alright, so when I just sum up all the terms present in this sequence up to n terms, and I just got an answer, and that answer should be equal to the square of this n. Okay, I have to prove that this equation is really correct or not. So I'm going to take the support of my mathematical induction process. Okay, so in the step 1, what I have to do, you know that the very first number in the natural set is 1. So I have to first of all show that this sequence, general form of this sequence 2n minus 1 is equals to n squared when I substitute n equals to 1 here. So this is the very first step of my mathematical induction, that is, I just prove both these sides equal with the help of the very first number of the domain of this function. Okay, so let us do the first step here. So here I've just written the very first step, that I just prove the two sides of the series equal by putting n equals to 1, and n1 is the very first number of the domain of this function. Okay, of this function. So I just find out that yes, it is true. So because both sides are equal, so the step that I'm going to write is that the sentence that I'm going to write is that subjective t of n, this series is true for n equals to 1. Okay, now move ahead to the next step. In the next step, I'm going to show that it is true. If it is true for any number, then it is going to be true for the very next number as well. Okay, so I'm not going to pick up any numerical value. I just assume a general way, and I just take a general way, and I just say that let the particular series, this series is true for n equals to k, then it should be true for n equals to k plus 1. That's what I have to do here. So my hypothesis is that in the next step 2, I'm going to show that let 2n minus 1 series of 2n minus 1 is true for n equals to k. So let's write down. So after performing the first step, that is p of n is true for n equals to 1, we move ahead to the next step, and we just say that this is our hypothesis that p of n is true for n equals to k as well. So I have just written over here the series in this form. At the place of my n, I just just put down the k over here, and I just said that this is true. Okay, this is just my hypothesis. Now what I have to do over here in order to make it true for n equals to k plus 1, which is the very next number after this value. So you see what I have to do, what exactly I have to add at both sides. So you see, when I put k plus 1 at the place of my n over here, what form I'm going to get, let's see in rough. So you see, so I'm solving. So this is something which is equivalent to this. Okay, so I have to add this value at both sides of this series equation. Okay, so once when I add up this value 2k plus 1 at both sides over here, so I'm going to start solving the right hand side, and after solving it should give me a form of k plus 1 whole square. When I substitute k plus 1 in the place of my n, it gives me k plus 1 whole square. So after solving I should get that answer. So let's have a look what we have to do. We have to add up 2k plus 1 at both sides. So let me write down the two values over here. So you can see now I've just add up 2k plus 1 at both sides over here. So now things is getting quite easy over here for me. You can see that this is an expansion of your k plus 1 whole square formula. So according to your, if you just recall that algebraic identity of a plus b whole square in your mind, you come to know that it is equals to a squared plus 2ab plus b square form. So it is exactly the expansion of one of your algebraic identity. So I'm just going to collapse, or I'm going to close this thing, or I'm just going to factorize this thing. I'm going to get something like this. Okay, so once when I just So once when I just applied the algebraic identity, this one over here, I adjusted it. Also, you can perform the midterm breaking if you want to. You come to know that it equals to k plus 1 whole square, which is exactly the format of your n square. Okay, so once, according to the hypothesis, if this series, the given series, is true for n equals to k, then it is true for n equals to k plus 1 as well. Okay, so according to your mathematical induction, the given P of n is true for all natural numbers. So that's it. That's how you just make your conclusion on the basis of your mathematical induction. So you can see that mathematical induction is a way of inducing your conclusion. Okay, you just induce your conclusion on the basis of the hypothesis. Okay, so let us look down to another example. Okay, here you go, another example, and you have to show that the summation of this of the terms of this sequence, which is a series, forming a series, should be equal to this value. Okay, so you know that this is a sequence function, and the domain of the sequence function is your natural numbers. So you're going to prove this general form equals to this form for n equals to 1. This is the very first step. So let us substitute n equals to 1 at both sides over here. Let's see, are we getting an equal answers or not? Okay, so in the first step, for n equals to 1, you just substitute n equals to 1 over here at both these sides, and on solving, you just come to know that both sides are equal. So given series, this P of n is true for n equals to 1. This should be your statement in the very first step. Okay, now in the next step, you're going to apply a hypothesis that assume or suppose that this series is true for n equals to k. Okay, this is our supposition, this is our hypothesis, whatever you say. So let us put down how this series is going to look like when I substitute n equals to k over here, and after that I have to show that it is true for n equals to k plus 1. So let us write down that, and this is going to be our second step. So that's how I have just written over here that let p of n is true for n equals to k. So over here, wherever I'm having n, I just placed k over there, and it is looking like this. Okay, that's how it is looking like. Now you see what I have to add at both sides so that the same equation is going to be true for n equals to k plus 1. It is going to prove that yes, it is true for n equals to k plus 1. So what exactly I have to add at both sides? For that purpose, I have just told you a technique in the previous example, that what you have to add, you just have to see the general form of your series present at the right side of your equation, and is n into n plus 1. So wherever you are having your n, you just put down k plus 1 there. So it is going to look like this. Okay, so we are going to know then what we have to add at both sides. So okay, so I'm sorry, wherever I'm having my n, it is k plus 1, and then I'm having n plus 1, so it is going to be k plus 1. This is my n, and this is a plus 1 of the formula. So it is going to be k plus 1 and k plus 2. Okay, so this is something that I have to add at both sides of this equation. Okay, oh, my ink spread up over here. So okay, so I have to add k plus 1, k plus 2, this value at both sides. Okay, so let us write down. Okay, so I have just add up the k plus 1 and k plus 2 at both sides of this equation, and I'm just having this. Okay, now I have to simplify the right hand side of this equation. Okay, and on simplification, let's see, are we getting the format of this type or not? So let's see, and it is definitely going to come. So let us solve this thing. Over here you can see that in both these terms I'm having k plus 1 and k plus 2 common here. So I'm going to take it out, and let's see what is going to left inside the brackets. So when I take out these two factors, the common factors inside the bracket, over here in this term I'm having just k upon 3 left, and over here in this term I'm just having 1 left. Okay, so what I have to do, I just take out the LCM of this thing, and let's see what is going to be. That's how it looks like. Okay, and then you can see that you can write this 3 outside exactly in the format, excuse me, so exactly in the format like this. Okay, so you can write in the way. So I have just written this 3 in the denominator in the starting, just to give the format, and I'm having these factors. So if I just organize these factors exactly in the format of n plus 1, as I'm taking my n equals to k plus 1, so I can write k plus 2 in this way and k plus 3 in this way. So here, if you can see that if at the place of k plus 1, when I just put my n, I'm exactly having the same format that is mentioned in the question. Okay, this is k plus 1, this is k plus 1, this is k plus 1. So you see the given p of n is, if it is true for n equals to k, then obviously it is true for n equals to k plus 1 as well. Okay, so according to your mathematical induction, therefore, the given p of n, this is your p of n, this is true for all types of natural numbers, for all natural numbers, I must say. So that's what your mathematical induction is, and that's how it helps in proving certain series, certain equations in the number theory. Okay, so that's all for today, and just if you people find this theorem, this video helpful in understanding the concept, then I appreciate if you subscribe my video, and so that you will remain tuned for the upcoming new launches. So thank you very much, and I'll see you in the future with some more examples on mathematical induction.